Welcome to Module 3, Hydraulic Pressure and Flow. Pressure in a hydraulic system is determined by resistance to flow, the load, what it is you're trying to do. The components, valves, viscosity, and all contribute to resistance, but are not that significant. Primarily, it's the load, what you're trying to do. As flow continues, pressure builds until the resistance is overcome and we're able to lift, dig, tow, or whatever it is we're wanting to do. Work begins when the pressure of the fluid overcomes the resistance of the load. Relief valves keep pressures from exceeding maximum limits of component and maintain constant pressure. Pressure is measured in force per unit of area, such as pounds per square inch or kilograms per square centimeter. Force is the outcome of fluid pressure being applied to an actuator. Linear force is measured in pounds, kilograms, or newtons. Rotary force is measured in foot-pounds or newton meters. Varying amounts of mechanical force can be extracted from a single amount of hydraulic pressure. The output force of a cylinder is dependent on its diameter, which is where you would get the surface area of that cylinder's diameter. This figure right here is a really good illustration of what I will term as multiple force multiplication. We've talked about force multiplication, using something small to lift something big. So notice a constant force input. In this example, looks like a brake pedal going to 3 different cylinders. So we have, notice a constant force, the foot pushing on the pedal, of 270 kilograms is transferring and directing energy to multiple actuators with varying areas to create selective output forces for specific tasks. I wonder if you could, looking at this figure, could you give me the what we called the other day the force factor? For instance, 270 input kilograms in a smaller cylinder, in a smaller cylinder is creating 45 kilograms of output. Now, to find what the force factor is, and is that twice as much, half as much, is you divide the output force by the input force. In this case, to get this force factor between here and here, you would divide 45 by 270 kilograms, and I think you get 0.17. So that makes sense because you're going to a heavy or a greater force, and it's actually going to a smaller cylinder face area, which would actually reduce the force of the input. The output force would be less than. So you're regulating in addition to transferring energy. The 270 kilogram input here to the center piston has an output force of 270 kilograms. So look at there, 270 divided 270. That's a 1, force factor 1. In other words, it's direct. It's the same. The third one, however, is pushing in with a smaller force than the output. So we have 270 kilograms of input force, and we are creating 740 kilograms of output force. So what is the force factor? 540 output divided by 270 input. Add that calculated. 2. That's twice as much. So we're getting 2 times the output as we're putting in input. 540 is twice 270. Where is it useful to come up with the force factor? Let's take this easy one here. A factor of 2 can be applied in other situations when you are just looking at a situation and you have a force factor of 2 to 1, let's say, and you are applying an input. This is just coming out of off the top of my head. You're creating an input force of, let's say, 5,000 pounds. What's going to be your output if you have a 2 to 1 force factor? Your output force is going to be 10,000 pounds because it's twice the input. So that's like a shortcut. There are calculations in every situation, but when you have these force factors, you can look at, for instance, the distance traveled. If you have a 2 to 1 force factor, and you're going to get, and you push it down 10 inches, you're actually only going to move 5 inches at the actuator. So you're going to lose distance by doubling your force. You're going to cut your distance in half. And that applies in all of the situations. So moving on. Here we're talking about flow rate and speed of the actuator. This is where I have a little bit of trouble accepting that it's it's in direct proportion. In other words, I'm looking at the PowerPoint here, and I guess you are too. I have some notes though I want to read after talking about this. The PowerPoint says the speed at which a load can be moved depends on the delivered flow rate and the size of the actuator. Well, that kind of makes sense to me. But if the actuator is much larger, the flow rate's going to slow down. And I'm not so sure that you're going to get that 1-to-1 ratio. But we will keep it as it is. The speed at which a load can be moved depends on the delivered flow rate and the size of the actuator. Now that's where they're talking about. You would, if you're so many gallons per minute, it's going to take you so long to fill this larger actuator up with fluid until you meet resistance. Only when you meet resistance where you start building pressure. So I'm thinking there may be a little differential instead of a 1-to-1, like the flow is equivalent to this, the hydraulic flow is equivalent to the speed of the actuator. In other words, there's a direct relationship. I'm just not sure about that. But we're gonna go by what the book says. Hydraulic flow is normally produced by using a positive displacement pump, and occurs when there's pressure differential. Well, it's got these this little simple illustration of how oil flows from a high to a low pressure, and we need a pressure differential. Here you have it blocked off, so this pressure is the same as this. Here it's open, so you're going to have a pressure drop from high pressure to low pressure. Take this with a grain of salt, because this is not the inlet of a pump. If it was the inlet of a pump, you would actually have, you could have a negative pressure or close to a vacuum here. But this is just going down the road. Uh, you would have a high pressure upstream than downstream. It's just trying to say that flow kind of seeks the path of least resistance, as all liquids and gases do. So I'm going to leave that alone. But there's a question that asks about this in your essay questions in your modules. So I'm going to go over a little scenario that talks about using a positive displacement pump. Let me just read it. It says a positive displacement pump creates a low pressure at the inlet. So we're going to get a pressure differential. At the inlet, lost my place. At the inlet, bringing fluid out of the reservoir through the pump and into the system. Now, when it gets on that side of the pump, it's going to be flowing, and it's at some point in a continuous flow. The fluid meets resistance from the system and the actuator, the system being all the hoses and valves and things that it has to go through, and also the viscosity of the fluid. All of that adds to resistance somewhat, only it's just pretty magnificent. But when it comes in contact with the actuator or the piston, the pressure buildup of the fluid, because the flow has decreased or come almost to a stop, but the flow has slowed, but it's still continuing to flow. So the pressure is continuing. The flow is decreasing, so the pressure will increase until the actuator opens and allows the fluid to flow back into the reservoir. The flow and pressure are regulated to maintain this differential. That was a little bit of a description for, you can find that in your book. I think some of that's my own words, I believe. But it's just like the intro. I'm looking for something of that nature in that essay question. Okay, let's see what we got next here. Here we go, flow rate and speed of actuator. Well, here again, I'm not sure about that, but there is a relationship between the rate of flow and the speed of the actuator. So force is the outcome of fluid pressure being applied to an actuator or cylinder or motor. A cylinder outputs a linear force when fluid pressure is applied to its piston, and a motor outputs a rotary force, which is called torque, when it receives pump flow. Linear force is measured in pounds, kilograms, or newtons, and rotary force is measured in foot-pounds or newton meters, which is the amount of rotational force that's 1 foot or 1 meter from the center of the rotary actuator shaft. So that's a little ditty on what they're talking about, the rate and speed of the actuator, because a pump motor, this rotary flow would be operating a pump motor that in turn would be operating an actuator, or it's the same thing. That rotary flow could be applied to a torque converter, like in an automatic transmission. So when the flow rate to a linear actuator is increased, the rod or actuator travel speeds up. If the flow rate to a rotary actuator is increased, its output shaft speeds up. So there we have that out of the way. Positive and negative pressure really don't talk, nor does the book talk about it. About the only two places you'll have a difference is positive. You'll find positive. The only place you'll probably find a negative pressure is at the pump, a hydraulic pump inlet. because it's creating a vacuum which allows the reservoir fluid to be, I'll use the word sucked, but it's just a pressure differential up into the pump, where the pump starts moving the flow. And then here we go again into the cycle where the flow continues until it meets resistance. Then pressure begins to fill in the fluid until it overcomes that resistance, which is usually the load that we need. Load, when I say load, the action that we need for the actuator to do: dig, pull, tow, whatever. Talks a little bit about what atmospheric pressure at sea level is, and uh, it talks about these gauges. I don't have any questions about this, but just remember that if a gauge is calibrated to be absolute gauge, it would be read 14.7 pounds per square inch at sea level. Positive pressure, this is obvious, occurs when you're above zero. Negative pressure occurs when fluid pressure falls below zero. So like I say, the only place you're probably going to find that negative pressure is at the inlet of a pump. From the other side of the pump all the way to the actuator is going to be increasingly positive pressure. Now, all of this depends on your consistency in fluid flow, gallons per minute. That has to be maintained by a regulator that's measuring pressure to keep measuring flow, which is different than measuring pressure. Measuring gallons per minute, it keeps it at a constant flow to maintain the system. I think that's all I have as an introduction to Module 3. That's getting into another module now. So we'll see you in week 3 at some point. There may be some more videos or announcements between now and then. In the meantime, let's have a good time with Module 2. Thank you.